Hello. In the Taylor series section, we are going to look at what is a Taylor series. And so, suppose we have a function and we want to know its power series representation. In 11.1 and 11.2, when we were approximating functions and we were looking at power series, there was this connection of functions can be represented by a power series. And now we're actually asking that question, what is the power series that we can represent a function with? And that power series has a special name and is known as the Taylor series. And we actually already saw this series, but we are putting the formal name to it, that a Taylor series is the series of the sum n equals 0 to infinity of f sub n at a all over n factorial times x minus a to the n. And we've seen some of these terms when we were approximating functions. This would be f of a over 0 factorial x minus a to the 0 plus f prime of a over 1 factorial x minus a to the first plus the second derivative at a over 2 factorial x minus a squared plus the third derivative at a over 3 factorial x minus a cubed, and so on. And this one, because it's a series, continues on forever. It's an infinite polynomial where those coefficients are made up of the derivatives. A Maclaurin series for a function is just the Taylor series if the center is 0. So this is the series n equals 0 to infinity of f of n at 0 over n factorial x to the n. This would be f of 0 plus f prime at 0 over 1 factorial x plus the second derivative at 0 over 2 factorial x squared plus the third derivative at 0 over 3 factorial x cubed, and so on. It's just the center is 0. A few notes about these is they're used to represent functions. The power series and a function can equal each other on an interval. But if f has a power series representation at a, then that power series must be the Taylor series of f centered at a. So if there is a power series representation, that power series representation is the Taylor series. However, it is possible for a function to not equal its Taylor series. A quick example of this would be the function that is the absolute value of x. If we were to find the power series for f of x at 1, so let's say a equals 1, then when we look at the function f of x equals the absolute value of x, f at 1 is 1 plus the first derivative of the absolute value function is 1 And then I can't actually, well, I can take more derivatives, but all the derivatives after that point, because the absolute value function is just a line when we're looking in at one, the second derivative of a line is 0, and the third derivative of a line is 0, and the fourth derivative is 0, and so on. And if we simplify this down, 1 plus x minus 1 is just x. So the power series, or the Taylor series, is Taylor series for the absolute value of x is x at a equals 1. But we know the function of the absolute value of x and the function y equals x are not the same function. I have now sketched y equals x in red, and we have y equals the absolute value of x in black in that picture. They're not the same function. So a function may not necessarily be its Taylor series. But if we zoom in on this picture, the absolute value of x and y equals x do equal each other for some interval. So what it's useful to know is what are the values of x when the power series equals the function, and also what values of x does the power series converge. The values of x for which the power series converges, we named this in a couple sections ago. This is known as the interval of convergence. And a majority of the time, not always, but a majority of the time, the interval of convergence and the values of x for which the power series of f equals f is the same thing. There are some examples as to when this doesn't work, like the absolute value function. But in general, those intervals are going to be very similar. All right, so let's take a look at the first example of this, of finding the Maclaurin series. Maclaurin means a equals 0 for f of x equals e to the x. So we're trying to find the series n equals 0 to infinity of f n at 0 over n factorial x to the n. So let's find a few derivatives. The first derivative of e to the x is e to the x. The second derivative of e to the x is e to the x. And no matter which derivative I take of e to the x, I keep getting e to the x. And if I plug 0 in to e to the x, because our center is 0, we get e to the 0, which is 1, all the way down. So no matter which derivative I'm taking, the nth derivative of f at 0 is 1. So all of these are 1, meaning this power series is n equals 0 to infinity 1 over n factorial x to the n. We can also write this as n equals 0 to infinity x to the n over n factorial. Finding the interval of convergence, we actually did this a couple sections ago. We're going to do it again quickly. And that is running the ratio test. to find the interval of convergence. So the ratio test has us set up the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial, all over x to the n over n factorial, absolute values, keep, change, flip. We get x to the n plus 1 times n factorial all over n plus 1 factorial x to the n. And how this simplifies is we end up with x over n plus 1. This limit does not matter what x is. X could be 5, x could be 2000. X is a number that isn't moving, whereas n plus 1 is going to infinity. So this limit is 0. Since 0 is less than 1, by the ratio test, the series n equals 0 to infinity x to the n over n factorial converges for all x, making the interval of convergence negative infinity to infinity. At this point, we don't know if e to the x and this series x to the n over n factorial are the same on that whole interval, but we do know x to the n over n factorial has an interval of convergence of negative infinity to infinity, meaning does not matter what x I plug in, I will have a converging series. All right. We will take a look at more examples in the next video.